Good afternoon, student of the course 4006. And here we are doing a little bit of practice with integrals. And by now you pretty much have a good idea of this type of integral, and where there's the denominator is based on a polynomial expression, and so the numerator. And I have here two examples, and let's see what will happen. For example, very quickly you will find out that the denominator here is the denominator is order of 2, the numerator is order of 1, and you will say, hey, the difference denominator minus numerator is about 1. So that somehow has to do with an integral that has to do with logarithm. Well, yes and no. We have to be careful here, and let's see what will happen, or what it requires to convert this to what we need to do. Like, for example, you might start by saying, let's do a change of variables so that the denominator here is x squared plus 2x minus 3. So the differential of that variable du will be 2x plus 2 and all that time dx. All right? There's a problem here, because basically you will not be able to separate the variables properly, okay? And that creates a problem, because you will end up with something like this: du over 2x plus 2 equal a dx. See? And that's a problem. I can certainly do a little bit more, and let's say that if you multiply by x here and you get x here, so you start to take a look, but now you have x here and an x here as well, and a new variable u, and you have another variable here that is u. It seems like you are not going anywhere. Actually, we can start so that this part start to look more like the numerator. You multiply by x, so you get x du over 2x plus 2 equal x dx. If I substitute this definition here in my integral, so it would not look good at all, because definitely I have to somehow get my value of x from the definition of u, which is already a quadratic expression here, a polynomial of the order of 2. So going through this avenue for this integral it's not gonna look pretty. Now, what's the difference between this integral and this one? Well, the difference is that, again, you can see that the denominator is order of 2, the numerator is order of 1, and the difference between the denominator and the numerator is 1. So that definitely will look like a logarithm integral. And let's see if a change of variable will do that. So you end up with x squared minus 3. The du here will be 2x dx, and now, as you can see, I have an x dx right here at the top of it, so it's easy to say that du over 2 is x dx. And now I can definitely substitute by definition of x dx is du over 2. I can put the 2 back here, and what I have, x squared minus 3, but that is u. So as you can see, this will be 1/2 the logarithm of u equal 1/2 logarithm of u, but u by definition is x squared minus 3 plus, if we are integrating without any limits on our integral, plus c. So this is basically the result for this integral, as we'll have learned before. Now, the problem here is that I cannot separate the variable between the x and the u, and that created a problem. So I have to use a kind of a different technique to deal with this. Let's see what technique we can use. And so let's copy that again, and let's see the new technique that we're going to learn when things don't go the way we want. Let's put it right here. So here we are. Uh, we cannot separate into new variables, the polynomial here, so we have to do something different. And what we can do certainly, is try to expand, to factorize, actually is the word, to factorize this polynomial here such that we can do something like this. And we need to find a value here and another value here, and the sign. What would be the sign that we need to have in the middle? If I can factor this polynomial, I will be able to use another technique that we will learn in a second. So the idea is, can we factor this? Well, you certainly, if you have an idea, I mean, it might look like you can do something like this. For the denominator, you might be able to say, hey, I need a negative 3, but a positive inside. So you might say, hey, I might need a positive 3 here and a minus 1 here. So 3 by minus 1, that would be minus 3. Then, but if I have an x here and an x here, so I have, let's see, x minus 1, x plus 3. Seems like that might be the factor for this guy here. So that would be x times x, that would be x squared. 3x, x minus 1, that will be minus x. So that would be 3 minus 2, that would be positive 2x, and 3 by minus 1. So I was able to factorize, this guy. That's good, because then basically what I'm doing now is doing this integral, x dx divided by x plus 3, x minus 1. See? That's how simple you get. Now, this, when you can factorize the denominator like this, then you are in what is known as partial fraction integration. Okay? But going back to this issue here, let's say that you don't know how to factorize your polynomial. Right? It's a little bit complicated, but again, it's a square polynomial, order 2. You can certainly do two things. Either you can use the quadratic, or you can complete the square. Complete the square. What the hell is that? Well, complete the square is a technique that, for example, let's complete the square for this guy. 2x minus 3. That's my polynomial.
We interrupt this program to bring you a special report.
So we want to complete the square of a function. Let's see, of a polynomial order 2. And let's write any polynomial here. Let's say that we have something like ax squared plus, okay, let's use that b x plus c. And we want to complete the square of that. The first things that you should do is, like, for example, there's a letter here in front as a constant value, right? So you should divide by that constant so that this looks more like this. It's gonna look like, let's say that we divided that polynomial by that constant that is here, but also we multiply by the same constant. So basically we are not doing anything. We are not changing anything. But when we do that, we end up with something like this. A. Now, if we divide by A, so that will end up a squared plus b over a x plus c over a. And that's it. So now, careful here. What we want to be sure is that there's a 1 here for what is coming now. The idea is that you will do like this. It's going to be the letter a there, I mean the constant a, times x plus b over a divided by 2. All that has to be squared. And so if we put a bracket here, and we end up like c over a minus. Now, here's the part that you have to be very careful. All this part here, if I fix this so it looks better. So you have, as I said, b over a, but that's also have to be multiplied 1/2, right? There we go. Now, c over a minus, now all these have to be squared. So you will end up with 1/4, right? The 2 squared, b squared over a squared. And we close the bracket. So what we are saying is that this that you have here is equivalent to this. All right? And why we want to do that? Well, you complete the square basically because here everything is a constant. This is a number. At the end of the day, this is going to be a number. And you want to end up with this square part here. All right, let's do that. Let's do an example. Actually, let's do the example that I open this announcement. X squared plus 2x minus 3. And we want to complete the square for this function. Complete the square. Now check what we have here. It's a 1. That's not a big deal, right? Being a 1 there, you know, dividing by 1 and multiplying by 1, it doesn't make too much sense, right? But that's basically what the formula said. So basically, what you're saying is this stay the same, not a big deal. So what you have to do is apply what is said here, particularly this part here, that in this case the constant a, which is here, is 1, not a big deal. So you end up with x plus. Now, here is b over a. Remember, a is a 1, so but b is 2. So that's 2 over 1, but that would be divided by 2. So that end up to be 1, and all that square. Now, here's the part. Careful here. You have a minus 3. Let's put what the sign there. It's a minus 3. And then you subtract this part here, but square, obviously. Minus 1 square being 1. So at the end, what we have? X plus 1 square minus 4. And that's the result. That's the final result, and we have complete the square of this function, which is kind of nice because one thing that this lead to is to the roots of this function here. What are the root? You solve this, and you're going to get the root very quickly. Like you are using the kind of the quadratic function, right? The quadratic formula. If you want to find the root, meaning that this is equal 0, basically you will have x plus 1 square equal 4, and then you have x plus 1. If you take the square root in both sides, and remember this is plus minus here, end up being equals plus minus square root of 4, that's 2. So you end up with x equal, either put this one back here, that would be minus 1 when you are analyzing the plus 2, so that would be plus 2, or x, one root would be minus 1 plus 2 equal 1, and the other root will be minus 1 minus 2, and that would be minus 3. So you got the two roots there. Finally, if you want to factorize that polynomial, x2 plus 2x minus 3, that has to be equal to what? So let's put here the factor. Remember, you just change the sign here, so that will be x minus 1, and the other one will be x plus 3. And that's it. And these are the factors for this polynomial. Because if you want to, you want to be sure that they are, just do the math here. That will be x times x. That would be x squared. I'm sorry, x times x times 3 plus 3x minus x minus 3. So the result will be x squared plus 2x minus 3, which is what we have here to start with. So we demonstrate those roots are correct. Now, let's do a more complicated exercise so that we get this business of completing the square correct. Like, for example, let's say that we have 4x squared plus 12x plus 9. we want to complete the square of this. So that will be, remember, you don't want to have that 4 there. So you divide by the whole thing by 4 and multiply by 4. So that end up being 4. That would be x over 4 plus 12x over 4 plus 9 over 4, right? So at the end, you end up 4. What happened? 4 over divided by 4, that obviously that would be x squared plus 12, that would be 3x plus 9, 4. And that's it. Now, we haven't completed the square yet. We are in the process to do so. Because the final result will be 4 here. Open a bracket here, because this is parentheses for the square part. That would be x. Now, remember, 3 over 2, because this is the value of b, and that has to be divided by 2 according to what we have here. See? I already divide by a, the whole expression, and that's what this 12 by 4, that's what the 3 come from. Now, all this part here, x plus 3 over 2, that has to be squared, plus 9, 4, minus this part here, but has to be squared, minus 3 over 2 squared, close this bracket here. This parenthesis go with that. So the result, the final result of this would be 4 x plus 3 and a half, 3 half, 1.5 squared, plus, now let's work the math here. That would be 9 over 4 minus 3 squared, that would be 9, and the 2 squared, that would be 4. And this is very interesting because this problem will end up like this. 4, let's put a bracket here. Let's keep the bracket for a second. I still have the x plus 3 over 2 squared, but here plus 0. What that really means is that this is the result. The final result is 4 times x plus 3 and a half x plus 3 over 2. And these are the factor for that polynomial. Which polynomial? Let me close this a little bit. This one shown here. So this shown here end up looking like this. All right. So we got that too as well done. Maybe I can do one more. Let's do one more. And we close this special bulletin. Let's do one again, kind of complicated in the sense that we have 4x squared, let's say plus 20x plus 25, and we want to complete the square of this. So obviously the first thing that you do is divide by 4, the whole expression multiplied by 4, so you end up 4 divided by 4, that would be x squared plus 20, in this case divide by 4, right? So you got let me do it here. I'm gonna do it here. I got x plus 25 divided by 4, and that's it. So if I simplify this, 4 x squared plus 5x plus 25 divided by 4, and that's what I got. So what's next? Next is we want to complete the square of the part that is inside. So that would be 4x. Let's open here a bracket. And here you have a parenthesis. That's for x plus. Now this part here is 5 over 2, and that has to be squared, plus 25 over 4 minus 5 over 2. But that 5 over 2, the whole thing has to be square. Close the bracket. And we solve for the end of this. That would be 4, bracket, parenthesis. This part will stay. But this part needs the math. That would be 25 over 4 minus 5 squared. That would be 25 over 4. And this example also end up being this part 0 here. But the final result for this example is 4. I can leave like that. X 5 over 2 times x simplify over 2 if you want to. So these are the factors for solving this problem here. The final result of our problem when we complete the square is that one there. All right. Do we have time for one more? Yeah, let's do one more, and that's it. This is the last one. Let's work on this one. Let's say that I have something like x squared minus 2x plus 17 equals 0. So how we work this problem? Well, the same as the other. Remember, here is a 1. I don't have to change anything, so this is ready for completing the square. How do I do that? X here. Now I have a minus 2 here. Obviously, you divide it by 2, and that's going to be a minus 1. And that part is the part that has to be squared. Now, I have the 17. And this is the part that might confuse people. I'm basically, look like I'm subtracting a 1 here, but this one will become a positive 1 because it's negative by minus 1 by minus 1 in one point in time. That will be a positive 1. So you have to subtract, no matter the sign here, no matter the sign, you subtract that number. Square, remember to square it. Obviously, it's 1 square. So the final result here will be x minus 1 square plus 17 minus 1, that will be 16. And that's the end of the game, right? Now, we want to demonstrate that this result makes sense. How I do that? Well, remember x minus 1 square, so that, let's put it this way. X minus 1 plus 16. And let's see if this result here is the same as this one. All right? So x times x, that's x squared. X minus 1 is minus x. Minus 1 times x is minus x. And minus 1, that's plus 1 plus 16. So at the end, I have x squared minus 2x plus 17. That's precisely what we start with. All right? So if you are doing, now, as a bonus, let's say that you are doing an integration. Because this was like how you complete the square of a polynomial of order 2. So let's say that I'm doing an integration like this. All right. So I have this denominator here. Let's erase what is not necessary. There we go. If I'm doing the integration of that function that is shown there, how I do that? Well, basically, we just complete the square here at the bottom, and what's the result here? Is x minus 1 square plus 16. All right, and here is something that you have to pay a lot of attention. What's the order of the denominator? Order 2. What's the order of the numerator? Order 0. All right. The question is, can you factorize this more? And the answer you will see in a second. X minus 1 squared plus 16 equals 0. That will be x minus 1 squared equals minus 16. When you take the square root, it will not work. You are taking the square root of a negative number. End of the game, right there. This cannot be factorized anymore. Guess what? Do you remember a function that looks like that? You do. I bet you do. It has to do with inverse tangent. All right. How can that be that inverse of a tangent? How can that be? Well, it happened that if you let u equal x minus 1, what is the du? Du is the dx. Now, if you substitute this right here, you end up like du over u squared plus 16. Let's go for 1 second to the integral table and let's find out what is there that looks like this. All right, let's do that right now. How about this one here? See, 1 over a squared plus the integral of 1 over a squared plus x squared is 1 over a inverse tangent x over a. It's just the inverse, 1 over a, and that's precisely what we got. The inverse of the tangent will be the result of that at the beginning was kind of difficult, but then when you break it down, end up being very simple. So it's 1 over a inverse tangent x over a. Let's work back again on that. So the result here will be, if you are working on this, is 1 over a. The question is, what is a? A is 16 squared. Remember, a squared is 16. So a is 4. Right? When you take the square root of both sides, that means 4. So I have 1 over 4 times the inverse tangent of x, which in this case is u, over 4. I haven't finished yet, so that means it's 1 over 4 inverse of the tangent, in this case will be u, but u is x minus 1 over 4 plus a constant. End of this bulletin news. Right? We haven't resolved the integral. We are transforming the integral so that we get something that we can integrate later at a later time. So here we are. That needs to be equal 0. So how we work that out? But then if we use the quadratic, that will be minus b, if you remember, minus b plus minus b squared minus 4ac, where the number of the coefficient in front of the x here is a, this is b, and the last one here is c, right? So all that divided by 2a, and that will be the two results that we are looking, x1, x2, the two roots, right? So if I apply this formula, that will be, for example, for x1, that will be minus b, but that will be minus 2, and let's apply one sign. So excuse me, one sign here, that would be plus, and that would be 2 squared, that would be 4, minus 4 times a, which is 1, times c, that is minus 3, and all that divided, up to here, all that divided by 2a, but a is 1, all right? So x1 will be minus 2 plus, here we have 4, now minus, that will be positive, and that 4 by times 3, that's 12, that will be 16. So this result inside here will be 16, and all that divided by 2. So the first result will be x1 equal minus 2 plus the square root of 16, that's 4 over 2. So that will be minus 2, plus 2, sorry, plus 2 divided by 2, and that's 1. That's precisely one of the results that we got from completing the square. Now the other one, let's work it out. The other one, what is required is use the negative sign, all right? So that basically is the same inside, doesn't change, it's just the negative in the outside of the square root. So you will end up, the x2 result that we are looking will be minus 2 minus 4 divided by 2. And that will be minus 6 divided by 2, and that's minus 3. So here you have the two roots that we are looking, which is 1 and minus 3, all right? Which is the same that we got for when we use the procedure for completing the square, which basically this is simple enough that you can see what are the factors and get it done. What is important is that you factorize this denominator and that you now change your integral from this form to this new form in where the denominator was factorized. Now, how we deal with this? As I said, this is part of one of the cases that we're going to be working on partial fraction. Actually, this is what is called case A. The first case is when you can factorize the denominator, whatever coefficient that you have here. If you can factorize it, you know, then you are in the right way to do it. Like for example, let's say that you have a polynomial, something like this. Let's say that you have qx over px dx, and if you can factorize px such as you have something like x, I will say this is a general concept, x plus a, x plus b, x plus c, and so forth. You can factorize like that, then this is what is called case A, case A of partial fraction integration. Case A, right? That you can, and remember as well that px, the order of px gotta be higher than qx. If for some reason, this is to apply partial fraction. To apply partial fraction, the order of px gotta be higher than qx. See, very important. Like for example, the example that we are working, the order of the denominator is 2. The order of the numerator is 1. So, with that said, let's see how this looks like. We are here. We are integrating x dx over x plus 3, x minus 1. And that's what we have. All right. And we want to integrate this. What happens now is that you're going to use partial fraction to solve this problem. Very easy. You will do this. You will say that the function that we want to integrate is this one here, right? Is x over x plus 3, x minus 1. This falls under the case A of partial fraction, so you will do this. This is equal to one fraction, which is x plus 3, to another fraction that will be b plus x minus 1. See? So you are dividing these into fractions that when you add them up, then you will get the original. But the idea to divide it like this is because these are easier to integrate than the whole thing together. Because basically you can tell, if you know a and b are constant, if you take a look at this, you know how to integrate this already, because the order of this denominator is the order of 1, the order of the numerator is order 0, and you know now that that's definitely its logarithm. And so this one. So what we need to find now is what is a and what is b. To do that, then you multiply the whole thing by the denominators, so you end up here with x equal a x plus 3. If I multiply by the whole thing, x plus 3, x minus 1, plus b, x minus 1 times x plus 3, x minus 1. What's going to happen is x plus 3 cancel out, x minus 1 cancel out, and you end up with x equal a x minus 1 plus b x plus 3. All right? So, and that's what we need to solve. It's very easy to solve this system when you establish things like what will happen when x equal 1. Then the a disappears. You only have to deal with the b. What will happen when the x is minus 3? The b disappear and you only have to handle the a part. So it's very simple. Instead of solving two simultaneous equations for a and b, I'd rather solve one, and that by picking the right value of x, that will eliminate at least one of the variables. Like for example, when x equal 1, it means that if x equal 1, I have to substitute here back again, is 1 equal. When x1, the a is gone. So what I got, let's write it down. 1 minus 1 plus b. When x is 1, 1 plus 3. This part 1 minus 1, obviously 0, so you end up with 1 equal 4 times b. So that b is 1 4. See? Now what we will do now is get the, I know the b, how about the a? But you can do what you did already, but instead of picking x equal 1, I mean you pick x equal minus 3. If you do that, then you end up minus 3 equal a minus 3 minus 1 plus b minus 3 plus 3. Obviously this part is gone, so you end up like a is minus 3 divided over 4. Now this is negative as well. Minus 3 is negative, minus 3 minus 1, that's minus 4. So the result here will be a equal 3/4 positive. See? So that's now our result. Our partial fraction for this problem is this, is a is 3/4 over x plus 3 plus b. But what is b? b is 1/4 over x minus 1, obviously. X minus 1. See? And now we broke, I mean, the original integral that is shown here was broken in two parts. The first part, 3/4 over x plus 3, plus the second part, 1/4 over x minus 1. If you multiply this under a common denominator, should come back to the original part here. That's basically it. Let's see where we are now. Basically what we did is, let's see if I can. We convert my original integral, which was, let's go back and let's copy that. My original integral, that was this one, and we convert that integral into a form that, let's put it like here, somewhere here, so the original integral was this one, and we convert that integral to this one. That's basically what we did. All right. So by factorizing the denominator as shown here, and then knowing how to deal with this, that is a subset of partial fraction. As long as the numerator is less than the order of the numerator, less than the denominator, we are okay to use partial fraction. Otherwise, we will have to do the long division, right? And I did the partial fraction of the function, which is right here. So what I have to do now is basically, if what is here is this part here, so if this become this part here, then I can certainly do this, like for example 3/4 dx over x plus 3. I can break in this integral in two parts as part the partial fraction. That will be plus the integral of 1/4 over x minus 1 dx, and the the integration of the first part is straightforward, right? It's going to be 3/4 logarithm of x plus 3. The integration of the second part will be plus 1/4 the logarithm of x minus 1 plus some constant because it's general. You can definitely simplify this if you want to. I will leave it like that. No big deal, right? So this is the solution to this integral here, to this one here, is that is shown there through the process of partial fraction. As long as you can factorize the denominator, you are okay. Like for example, let's work another example of this. Let's open this big. So let's say that we want to integrate a function like this, x squared dx, and the denominator is x plus 1, x plus 2, x minus 3. The order of the denominator is order 3, the order, right? X to the cube. The order of the numerator is x squared. That means that this is definitely is under case A of partial fraction. I can break this function in partial fraction, meaning that x squared over x plus 1, x plus 2, x minus 3. Let's fix this. It can be broken into A, x plus 1, B, x plus 2, and C, x minus 3. There we go. Now, the solution of that is as simple as multiplying by the denominator here, the whole expression. Remember, we are converting these to some partial fraction that are very simple to integrate. If I am able to convert this part here to this, to break this into these 3 partial fractions, we will be in very good shape because it's easy to integrate this, and this. We know that if I can find A, B, and C, which are constant, this will be a logarithm, this will be a logarithm, and so the last one. See? Straightforward to integrate that. So let's multiply the whole thing then by the denominator, and you end up with x squared equal. Now, A, let's see, you have it in the denominator here is x plus 1, so you will end up here with x plus 2, x minus 3. Now, what happened with the B? Plus B. B will end up, you have an x plus 2, so x plus 2 here cancel out. You will end up with x plus 1 and x minus 3. And finally, with the C, you will end up like, let's fix this 3 here. You will end up, x minus 3 is there, so you will end up x plus 1 times x plus 2. That's it. So how we find A, B, and C? You can use the method that I told you already. If you, for example, put here x equal minus 2, A will be, with x minus 2 here, this will be gone, and so C. So you only left with solving B. How about if x equal 3? If x equal 3, then this is gone, and you find C. What happened with x equal minus 1? If x is equal minus 1, you can, this is gone, and you might find A. So that's how you will go to this, like which value of x will eliminate which variable. So when you put x equal minus 2, we know that A will not be required, and minus 2 and C will not be required. They are gone because you put -2, this is 0, -2, this is 0, so only you are only left with the b, which in that case will be -2 squared. That will be -2 squared equal to the only thing that is left, that is b times -2 plus 1, -2 minus 3. So you end up -2 squared, that would be 4, equal b minus 1 minus 5. So you end up 4 equal b minus minus, that would be positive 5. So the result for b is 4. That's the value. See? Now we will do the same for the other variables, and we will find those variables very quickly. Like for example, what happened when x equal -1. Now we're going to be testing x equal -1. When I test x equal -1, look at this. -1 will eliminate this part here, and also will eliminate the b part. -1 plus 1, that will be 0. -1 plus 1, that will be 0. So b and c are gone. I only left with the a part. So -1 squared equal a minus 1 plus 2 plus -1 minus 3. So you end up -1 squared is 1 equal a -1 plus 2, that's 1, and that's going to be -4. So the value of a is -1,4. Excellent. So we got that too. We got the b, the a. Now we need the c value. The c value, check how can you eliminate the a and the b. Obviously, you put x equal 3. This is gone. And so this one with x equal 3. So let's do that. When x equal 3, so you have 3 squared equal, remember this part is gone, the b is gone. The only thing left is the c part. So that would be c times positive 3 plus 1, that would be 4. Positive 3 plus 2, that's 5. So our result for resolving for c equal 3 to the square, that would be 9. 5 times 4, that's 20. So this is the end of the result. C equal 920. All right, that's the three values, and with those three constants calculated, then the only thing that we need to do is just to put those constants right here. See? So the first one, a, we said that the value of a is -1,4 over x plus 1 plus b, but b is 4 over 5 divided by x plus 2. Fix this, looks lovely. 4 divided by 5, and the last value is plus 9 over 20 over, and that would be x minus 3. All right, so we convert all these, the function that is here, into these three partial fractions. So, and these are the constants, a, b, and c for those constants. Now, if I integrate here, dx, obviously I have this part here again. So that means that all of these have to be integrated as well. Each one is a dx here. And so the same I'm doing here. That will be dx, dx, and dx. So the solution to this problem, if you allow me to copy things here so that this looks better, let's copy the whole this part here and erase what is not needed. So let's go here. All right, and let's erase what I don't need. What I'm saying is this part here, this integral here, is equivalent to this one here, so I can eliminate this part in the center that I don't need it, and just put this right here. So we are breaking this integral, which is very difficult to work with, into three very simple integrals. Remember, each one of these is a constant, so it can be taken out from the integral, and you only left with a logarithm here, another logarithm here, and another logarithm here. And that the solution for this integral is as simple as minus 1/4 by the logarithm of x plus 1 plus 4/5 times the logarithm of x plus 2 plus 9/20 times the logarithm of x minus 3 plus a constant, and that will do. So this is the solution of a kind of a difficult problem, but using partial fraction we are able to solve this within three simple integrals. So that's the idea, and that's what we call partial fraction class 1 or class A. Typically that's what they call it, class A, because there are four classes: A, B, C, and D. Class 1 is this one that I'm showing you, that is any time that you can break, for example, like this, any time that you can break or factorize a polynomial within its factors. That would be x plus 2, let's put it here, x minus 3, just to say something. That would be a partial fraction problem. And remember, the order of the numerator here is 0, the order of the denominator here is 2, the denominator. So in other words, it's very important that the qx, which is the order of the order of this numerator that might be here, be less than px, and px is the order of the denominator. It's very important that this is true before you apply partial fraction. If you apply partial fraction to this problem, basically what you're saying is we're going to break the function. Which function? This function that is here. Actually, instead of putting the signal equal here, let's work this out a little bit different. It would be 1 over x plus 2 x minus 3. And how I'm going to break that in partial fraction? Now, this case is case A, right? Simple case in where you can, when you have case A, you can break the whole thing like this: 1 over x plus 2, sorry for the one here, is letter A, plus b over x minus 3. As simple as that. So you multiply by the denominator here, that will end up like 1 equal a x plus b x plus 2. All right, so as I have shown you before, you want to eliminate the letter a, just say that x equals 3. When x equals 3, that will eliminate the a, and you will end up with the b. So that means 1 equal b, x equals 3 plus 2. So b is 1/5. Now, if I want to solve now for for a, how about x equal minus 2? That will do, because in that case 1 equal a minus 2 minus 3 plus, let's write this down so people understand, minus 2 plus 2, because I pick x equal minus 2, so this is gone, and what I'm gonna be left is with this part here. This 3 looks ugly, so that would be 1 equal a minus 5, so a equal 1 over 5 negative. All right, so the solution the solution of this, the constant for a and b, in this case will be a, I said that is negative 1 over 5 x plus 2 plus 1 over 5 over x minus 3. See? So what I'm saying is that we are able to break the function, which function? This one here, into partial fraction, and the function was changed to this, which is a lot easier to integrate than this part here. All right. So if I do that, basically what I'm doing is what I did above, right? You just integrate this multiplied by dx, right? That would be this part here. So if you are doing this, it's the same as doing this, which is the same as doing this as well. And the only thing that I care to do this integral is this part here, which is very simple to work because that the result here would be 1 over 5 negative times the log of x plus 2 plus 1 over 5 times the log of x minus 3 plus a constant for integration. I mean, you can simplify this a little bit more, and you can say that this is equal to 1/5 log the x minus 3 over x plus 2. You can do like that plus c. You can use a logarithm rule to simplify this and get it up to here. Since this is negative, it's the same. It goes to the denominator as shown here, and the 1/5 stay. All right. So that would be the solution for a problem like this. Again, that would be case A. All right. How about if you solve the following problems? All right. Let's see if I can solve this and let me know. See? How about that one? Oops. Try to solve that one and just let me know how will that work. Thank you. Have a nice day. Bye.